Oh, well, welcome back, Year 10. Welcome to the next lesson on our mains electricity topic. I know we did all our stuff about AC and DC last lesson. Let's look at how we get that AC into your house, okay? So I'll share my screen and we'll start getting this lesson going here. Let's do a share screen, and then let's get, there we go, there, title up. So this lesson is all about what we call the national grid. And it's all about, like I say, how we get the energy into our houses down the electric cables, that AC alternating current we were talking about. And it's a bit of a weird thought, and I sometimes think it'd be a bit weird if you can sort of imagine following the wire into a plug and down to the socket. Well, where do the wires in the wall go? Well, if you follow them out of your house, you'd end up going into one of the electricity cables that comes into your house, I guess. But then if I follow those wires over the hills and down the motorway to all sorts of places, where would I end up? I'd eventually end up at a big power station, maybe a nuclear power station, or one that's burning coal, or one that's burning gas, all those big power stations that generate electricity. And so we have to have all these special things built which take the power from the power stations to our houses. And we call that big system, we call that the national grid. So the national grid is all these cables which carry the electric power from the power station. And there are also these special boxes called transformers. Now, you may have seen transformers as you walk or drive into school, those big boxes fenced off which say warning, danger of electric shock, or danger electrocution. And those boxes are also a special part that the power flows through, and we'll need to look at what job they do as well. So if we think about our national grid, it looks a little something like this. The power starts off here. The power starts off in the power station. So we've got a power station. I'll see if I can do some writing here as we go along. So the power obviously starts off in the power station. Ooh, green's a pretty horrible color. We'll maybe change that. So it starts off in the power station. And then the power goes out of the power station and it goes through this first special box here, the step up transformer. So after it comes out of the power station, it goes through this special device here called a step-up transformer. Now, once it's been through the step-up transformer, that electric power gets sent through the great big cables you see being held up by pylons all over the country. So it gets sent along the cables. Now, before it goes into our houses, though, it goes into through another one of these special boxes here, another one of these transformer boxes. But you can see that this one isn't called a step-up transformer. It's called a step-down transformer. So it goes through a step-down transformer, and it goes through that before it goes into your house or maybe a shop or a school or a factory, the places where the electric power is used. So wherever it's being consumed or used, so it arrives where the consumers are, the people who are using them, or you could just say it arrives in people's homes there. So it's been on that whole big journey. The electric power comes out of a power station, then it goes through a step-up transformer, along the transmission cables, through a step-down transformer before it goes into our homes or whichever consumer it's going to. So that's its journey through the national grid. But actually, technically speaking, we say that the only parts of that which count as being the national grid are actually the cables. So the big cables there, and also the transformers. The transformers count as part of the national grid because those are the parts which are actually there to carry the power from the power station into your house. So when you're being asked about what is the national grid made from, we only count the cables and the transformers. So those are the national grid. We don't count the power station. We don't count the big pylons that hold up the wires. We don't count the houses that the power is going into. We don't count those. Only the cables and the transformer count as the national grid. So let's look at what's going on in some of those different parts of the national grid. We said that, first of all, obviously, the power station is where the power is actually generated. It burns some fossil fuels, so it might be burning some coal, or it might be burning some oil, or burning some gas. Oh, I'll switch to a nice pen there rather than a highlighter. So it might be some coal or some oil or some gas getting burnt in here, and that gets burnt. Well, that's a great bit of burning there. And then the energy from that gets sent along to this step-up transformer. Now, why would you want to do that? Well, let's talk about the job it does. Whenever the power comes out of the power station, it comes out of there at about 20,000 volts. Can be a bit more, can be a bit less, but it's in the tens of thousands. So maybe 10, 20, 30,000 volts coming out of the power station. Now, when that power goes through the step-up transformer, the clue is in the name here, a step-up transformer, it actually increases the voltage. So it comes out of the power station, but before it gets sent along the cables, it gets its voltage increased. It goes from about 20,000 volt to hundreds of thousands of volts. So it could be 200,000 volts. 300,000, 400,000 volts. It's up there in the hundreds of thousands of volts. So the step-up transformer increases the voltage. And the power goes through the cables at hundreds of thousands of volts. But before it goes into our house, it goes into the step-down transformer. Now, no big surprise. The name gives you the clue. The step-down transformer is going to decrease the voltage, and you actually know what number voltage it's going to decrease it to. In lessons before this, we said that the voltage going into our houses here in the UK was 230 volts. So our step-down transformer decreases the voltage. So you can see the power station burns the fossil fuels to generate the power. It sends it out there at tens of thousands of volts. So maybe 10, 20, 30,000 volts. It goes through the step-up transformer, and that increases the voltage to hundreds of thousands of volts. Maybe 100,000, 200,000, 300,000, maybe even 400,000 volts. But before it goes into our houses, the step-down transformer decreases the voltage to 230 volts for going into our houses. So that's its journey through the national grid. Step-up transformers increase the voltage, step-down transformers decrease the voltage. Okay, listen, you know a bit about the national grid now. So now it's time to go to the worksheet that comes along with this lesson. The worksheet there, called the National Grid Worksheet, is one which is just going to ask you to fill in some questions. Here we go, about the national grid. I just want you to do questions 1, 2, 3, 4, 5, and 6 on this one here, please. And for these questions, you're just going to name a part of the national grid which does the different jobs listed here. So question 1, for example, which of the parts that you're showing are not part of the national grid? So you can type your answers in the worksheet there. Now, I just want you to do questions 1, 2, 3, 4, 5, and 6 for the time being. We'll mark these later on in the lesson. But if you just do questions 1, 2, 3, 4, 5, and 6, you can pause the video now while you type those answers on. And when you're finished, come back, press play, and we'll do the rest of the lesson. So you can hit pause now. Welcome back from the lesson there. So last thing we need to do is actually look at why we bother with these step up and step down transformers. These transformers are really great big metal blocks that the power goes through. And as it goes through the transformers, they change the voltage. We said that a step up transformer increases voltage, and that a step down transformer decreases voltage. But the special extra fact we need to say about the voltage is that whenever the transformer increases voltage, it decreases the current. So a step-up transformer is making the voltage increase, but the current decreases. The opposite happens. With the step-down transformer, it decreases the voltage, like we said, but that actually makes the current increase. So we've got a step-down transformer. Although it makes the voltage decrease, decreasing voltage, we've got increasing current. So these step-up transformers are changing the voltage and the current at the same time. But why do we want to change this voltage? Why do we want our super high voltage in the transmission cables? You've got really high voltage up here, really high. We said it could be like 300, 400,000 volts. And why do we want lower voltage before it goes into our house? Okay, let's have a think. The thing is, if we sent the electric power through the cables at the wrong current, we get a big problem. You see, if we sent the electric power through the cables at a high current, like you can see in this picture, look what happens to the wires. The wires would get really, really hot. It is current that heats up the wires. So if I was doing that, I would be sending the power through the electric wires, and the electric wires would be getting super hot. Now, if they were getting super hot, a lot of people say, oh, well, I bet the problem, sir, is that the wires are going to melt. No, they're not going to get that hot, but they are going to get hot enough to be giving off lots of heat, and that means I'm wasting energy. All the energy coming off those wires is wasted energy that we want to come from the power station. If we think about all the energy that went into the power from the power station, we don't want that all coming out of the wires as the wires get hot. So the last thing we want is hot wires. Now, we said that hot wires were caused by a high current. So here's our trick. We use our step-up transformer. The step-up transformer increases the voltage, but that decreases the current. So that super high voltage in the cables means I've got a nice low current. Now, a low current means the wires aren't going to heat up as much. That means less energy is wasted. So that's why we use our step-up transformer. Our step-up transformer is there to make sure that we waste less energy as the current goes through the wires. But what about our step-down transformer? Our step-down transformer decreases the voltage. Why do I need to decrease the voltage? Well, if I think about it, I've got the power coming in from the cables at 200,000 volts. That's great because I've got a nice low current and the wires aren't heating up. But if 200,000 volts went straight into my house, that could be really dangerous. If something in my house has 200,000 volts, I could get a right zap, and I get an electric shock off that. Be really dangerous for an electric shock. It can also be more likely to cause fires in my house. Wow, the fires are really bad there. So the problem with really high voltage in my house is it's really dangerous. It could cause an electric shock, or it could cause a fire. So that's why we use our step-down transformer before the electric power goes into our house. So in summary, we've got our step-on transformer, which increases the voltage. I'll just get a fresh page to draw on here. So the step-up transformer makes the voltage go up. Oh, what a pen there, not a highlighter. So up go the volts. That means the current goes down. that means that there's less heating in these wires. So I've got less energy wasted. So that's why I use my step-up transformer. I use my step-down transformer to decrease that voltage back to my 230. That means it's much less dangerous and you're not going to get hurt by an electric shock, and it means it's less likely to start a fire. So, step-up transformer to increase the voltage, reduce the current, and mean there's less heating in the cables. Step-down transformers to decrease the voltage to make it safer, so we're less likely to get dangerous electric shocks or for fires to start in our house. Now you've now got enough information to fill in all the last questions on the worksheet we've got here. So the last part of the worksheet, questions 7, 8, 9 and 10 are on the worksheet there, which you can type answers to about why we use those transformers in the different part of the national grid there. So I know that says 9 to 10 there, but obviously it should say 7 to 10. I'll change that. So if you go and answer questions 7 to 10, once you've got those filled in, we'll mark them together. So if you can pause the video now, finish off questions 7 to 10, and then we'll come back and mark those. So you can pause now. Welcome back. If you've filled in questions 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, it's time to go through our answers and you can mark these and do your corrections on them. So question 1, which of the parts are not part of the national grid? So that will be things like the power station, the pylons that hold up the cables, or the consumers or homes at the end. Question 2, which part increases the voltage of the power supply? That's the step-up transformer. Question 3, which part decreases the voltage of the power supply? That's the step-down transformer. And question 4, which part burns fossil fuels? That's the power station. Which part of the picture has the highest voltage? That will be the transmission cables. So the electric power going through the cables has the highest voltage. And it says which part has a voltage of 230 volts? That's the consumers or the homes, where the power is going into the homes. 7, 8, 9 and 10. Let's have a look. What's the voltage of the mains electricity here in the UK? 230 volts. What's the frequency of the mains electricity here in the UK? 50 hertz. Why is a step-down transformer used before the power reaches people's houses? That gives you a safe voltage to prevent electric shocks, tick for 1 mark, or fires, tick for a 2nd mark. And finally, why is a step-up transformer used after the power leaves the power station? Okay, 4 marks to be had here. 1 mark, the step-up transformer increases the voltage, tick, and decreases current, tick. Now the lower current means there's less heating of the wires, tick. And less heating means less energy is wasted. Or you could say less energy is lost into the surroundings, or less heat is lost into the surroundings. So give yourself a tick for that. So 4 marks to be had on that last one. Now, before you submit this, make sure you've typed any corrections into your worksheet as well. Don't forget you can rewind this video to go through the answers. Your last job now the video is finished is there is one more worksheet attached to this lesson, and it's got some practice exam questions. You should be able to get that up there. It is some practice exam questions about the national grid. Now there are 1, 2, 3 questions in here, stepping up, getting from a foundation to a medium to a higher tier question. On those first pages. And once you've typed in all the answers, again at the end, you'll find the mark scheme answers at the end in red. So once you've typed your answers in, please go back and mark and correct your questions on those practice exam questions. And that is us done for the day, guys. Well played. That's our lesson. Make sure you submit your marked questions to me, both of those worksheets, so I can see how you're getting on. Please ask me any questions in the comments if you need them there. And that's it for the day. I'm going to stop sharing my screen and we'll get back to me. There I am. And I'll see you again next lesson. All the best.